Okay, suppose we have a complex plane, and on the complex plane we have a circle. The rate is A. So initially, let's assume the complex number is here. So this is the initial point of the complex number. And in general, that complex number, by using the Euler's formula, it can be written as A times e to the j times omega sub 0 times p plus psi, right? But if we look at only the imaginary part, so it's a projection onto the y-axis or the imaginary axis. So you can sketch the point, the curve, the point on the curve, point by point. So when time is 0, this is it. Okay? And when time equals to when omega sub 0 times p equals to half pi is here. And this is the projection. Right? So you can repeat this process until you construct the entire signal. And similarly, for the negative phase angle, we call this phase leg. We can start from here. This is the initial point. Okay? And then you move the complex number up. You move the circle along the circle. You can track the projection on the imaginary axis. Okay? And then next construct the signal, similar to what I did in the previous case. Now let me show you the complete figure. So when the phase angle is 0, this will be the signal. Okay, the phase angle is 0. So if I have a phase angle, positive phase angle, okay, phase angle greater than 0, I have a phase B. Okay, and then I have a phase left when the sign is negative. Right? The point here, I want to remind you why we call the phase angle is phase B or phase left. It's because of the starting point. For phase lead angle, the initial point is here. So this complex number move ahead sine degree. Okay? For the phase leg, this complex number move behind sine. This is the initial point. Okay? So that's why this is called the phase leg. And this is called phase B. Okay? So I think this is much more easier to understand the terminology. Alright, now for the cosine function given by the lecture note for the book is we simply change the cosine to sine. I'm sorry, simply change the sine to cosine. Sorry. Over here, I use sine function for illustration purpose. It's much more easier to illustrate the concept. But then for the cosine function, we have a similar way to interpret the signal. Okay? So, due to time limitation, I will just key point here. If I replace x of t by a times cosine omega sub 0, then this becomes the real part of Then how do I perform this projection? In this time, for this case, we project the complex number onto the real axis. Okay, so we have to look at the real part. That's the only difference between cosine function and the sine function. Got it? For the sine function, one more time, for the sine function, the projection is onto the y-axis or imaginary axis. This is real axis. This is imaginary axis. Okay, now the projection onto the imaginary axis, that's for the sine function. Because if you look at the equality, sine function comes from the imaginary part, and the cosine function comes from the real part. This is the real part, and this is the okay. Got it? So for the cosine function, you have to project the complex number onto the real axis. Look at the real part. Look at the real part. Yeah. So it's a projection onto the real axis. Okay, got it? Alright. If we consider maybe let me call this case 1. Okay, or let's call this case 2. For case 1, the complex number a times e to the j times omega sub 0 plus psi can be written as a product using the complex number product we have done in the previous hour. Is equal to e to the j times omega sub 0 times t, and then times e to the j psi. Okay? Now, if I combine the magnitude A with the phase angle e to the j psi, I can redefine this as a complex number x. And that x is called the phase. This is called the phase of the signal. Okay? Now, why we have to define a phasor? Why we have to define a phasor? Okay, for the case 2, let me finish this. Similarly, okay, the same actually. This is defined as the phasor x. So this can be written as the real part of the phasor times the sinusoidal signal e to the j omega sub 0 times e. So the phasor tells us two information. One is the magnitude of the signal from the A, okay, the radius, right? Okay. what can I do with the phasor, or why I need to discuss the phasor? Now here let's assume we have two signals. X1 and X2. Now, for some reason, if I have to consider the sum of these two signals, okay, so let's consider how do I come up with the sum of the two signals, X1 and X2. Oh, I'm sorry, let me use the same function first. Let me use the same function first. Now, if we use the cosine function, we sum up the two functions. Okay? It seems that we cannot tell too much from this expression. But one thing you can do is to expand the cosine function using the trigonometric function identity. Okay, that's one way to do it. So that's equal to, say, A1 times cosine omega 0 times Q plus cosine of sine 1. And then minus. Right, and then you can simplify that expression after that. That's one way to do it. But another way, or the second way, to do it is now we can use the phasor. So let's rewrite the signal X1 as the real part of U1 times is in what we have just learned previously. Why I want to do this? What can I get? What is the benefit of using this method? Now I can sum up these two complex numbers. Okay, now look at this expression. Both of them have e to the j omega sub 0 times t. That is the sinusoidal wave, sinusoidal signal on complex 10. Okay, so I'm going to subtract sinusoidal signal. So one more time, let me remind you, both x1 and x2 of t, both of them have the same frequency. They both have the same frequency, omega sub 0. Okay, omega sub 0. That's a frequency, radian per second. Now, if I write it in this way, you can see that this is similar to what we have just defined for the phasor, right? So this is equal to x1, phasor is 1 plus phasor is 2 times e to the j omega sub 0 times t. So now the, sorry, plus x2. Sorry. So now we only have to compute the sum of the two phasors, and then basically we are done. Okay, so let me finish this. Okay, so here we have two complex numbers, x1 and x2, because both phasors, x1 and x2, are complex numbers. So we can easily represent x1 and x2 on the complex plane. So let's assume this is the phasor x1. So the phase angle is psi 1. And the magnitude is A1. Okay? And we have another phasor x2. The phase angle is phi 2. The magnitude, or the distance, is A2. And then we sum up these two complex numbers. So this is the sum. Okay? So that's a benefit of using phasor. But personal opinion, now since we have a computer, we have a lab, we have software, so it's much more easier to use computer to compute those stuff, right? Okay, but these are fundamental knowledge you have to know. That's it. Okay? Question? Any question up to this moment? Well, then how do we compute the sum of these two complex numbers? And there are many different ways. And one way to do it is to use by using brute force. So let me write this. So let's equal to A1 sin 1, sin 1, J sin 1. Sum up the real part and the negative part. Set. Okay, so we have the real part and the imaginary part. Just by using brute force. But actually this is the same as the sum of two-dimensional vectors. Okay? Okay, any questions before we move on to the next topic? Okay. All right, now let's move on to the next one, which is going to be important. Now here, let's assume we have a stable linear system. Okay, what do I mean by that? Stable system or linear system? Stable means the eigenvalues of the system has negative real part. Okay, negative real axis, and the system is linear. It satisfies the linear property. So we will see that later on. Now the major issue here is suppose I have a sinusoidal wave. Sinusoidal signal. Suppose it is A times cosine omega sub 0 plus omega sub 0 times t plus t. And then go through the linear stable system. The output in steady state will be amplified by the magnitude of this transfer function. Okay, we will see that later. I will tell you what is the transfer function. Okay, h of s will be magnified by the magnitude of the transfer function of the system with additional phase. The phase angle is the phase of this transfer function. Okay, so let me write that quickly. This is called the frequency response. Stable linear system. Okay, let me give you a little bit detail here. Okay, let me ask a question again. I think I asked one once before. How many of you have learned or have heard the Laplace transform? How many of you have learned Laplace transform? You? No, I don't think you are the only one. Should be, yeah, some of you, right? Okay. How about Melissa? No? Okay. The others should have learned, right? Okay. Again, don't worry, we'll go through that later. Okay. So for the moment, let's assume you all have learned. Sorry about that. For the moment, okay. Now let's assume we have a function. Treat it as a function. That function is called h of s. And this is can read it as s minus lambda 1, s minus lambda 2, s minus lambda n. Okay, for simplicity, we use a scalar in the numerator. Okay, just for simplicity. Now, for a stable system, if h of s is stable, if and only h of s is stable, if and only if all the eigenvalues, the real part of the eigenvalues, are negative for all the r between 1 up to n. Okay. So if the transfer function or the system, okay, or values formula, whatever, if h of s can be written as a over s minus lambda 1, s minus lambda 2 up to s minus lambda n. S is a variable, okay? So this is a function of s. S is a variable. Okay, lambda I also are complex number. We define a stable system as the following. If and only if h of s is stable, that means all the real part of the eigenvalue lambda I are negative. So which means if you can sketch the eigenvalues lambda I on the complex, they will be on the left half hand. Okay, so suppose this is lambda 1, lambda 3, lambda 2, lambda 3, lambda 4, lambda 5, lambda 6. Okay, so all the eigenvalues are on the left half hand. Okay, that's the definition. So mostly you don't understand the definition of eigenvalue, that's fine. just treat this as a function. Okay, treat h of s as a function. And the roots, those lambda i's are the roots. Okay, one way to say that is lambda I, they are the roots of s minus lambda 1 of this equation, right? Okay, one way to say that is lambda I, those lambda 1, lambda 2, lambda n, they are the roots of this equation. And actually this is a polynomial in terms of s, nth order polynomial. Okay, there are a lot of mathematics here, but forget about that for a moment. Let's use a very simple case. S minus 1 times s minus 2. That's one example. Oh, sorry, plus 1 plus 2. That's one example. Another example, okay, let's see the second one. Okay, now this time we have complex eigenvalues, right? Okay, so in this case, let me write a case like this. So H1, lambda 1 equals negative, lambda 2 equals negative 2. So both are on the left out plane. And H2 of this. Another example. Now this time we have a second order polynomial in the denominator. So what is the eigenvalue lambda 1 and lambda 2? We saw the equation, okay? So what are the roots? Remember, the definition is the root. Okay? So lambda 1, 2. Is that right? I think everyone knows this one correctly. So for the moment, let me assume lambda 1 is defined as the one with positive sign. And lambda 2 with negative sign. Okay? Got it? So let's give you a better idea. That gives you a better idea of the stable system. Okay, now we have a stable system. And it is linear. Okay, after this moment, I do not define the linearity. Due to a time limitation, let me skip that. Okay, let's assume they are linear. Yes, but indeed they are linear. They satisfy the linearity property. Okay, let's just focus on the stability. Okay, now if I have a sinusoidal signal, for simplicity, let's use cosine of following location. Omega sub 0 times t. What is the output signal in steady state? So now you have a sinusoidal signal. To the system. Okay? And what do you expect? What do you expect? The output from the system. Actually, this can be done by solving the differential equations if you want. But if the order of the system, or if the order of the polynomial is I, it is very hard. It is very hard. Okay? But it's doable, even though it's very hard. a little bit complicated, that's all. Now, this is the theory. So let H always be a stable linear system. Okay? Then y sub SS of t defined as t approaches infinity. Okay, that's crucial. Of y of t, and then for this output y of t. Output. Well, input is u of t, let me say that. Okay. So u of t, that's an input to the system. And the y of t, that's the output of the system. Now here I'm a little bit sloppy. I'm a little bit fussy here. Sloppy. The input and output both are in the time domain, t domain, time domain. But H of S in the S domain. S domain is the frequency domain. But that's a convention. Everyone did this way. Okay? T is in the time domain. Strictly speaking, I am not allowed to do this. Combine T domain, time domain with the frequency domain as H of S. But that's a convention. Everyone in the field of control, they did this. They all did this. Okay? Because by using this notation, we know we are talking about a linear system. This is the linear system. If you write it this way, you know that is a linear system for sure. Okay, anyway, so let's go back to the theorem. If I have a stable linear system, H of S, then the output in steady state, this is the output. In steady state. Okay? By definition, that's the limit. As t approaches infinity, well, will be a times the magnitude h of j omega sub 0. Okay, so it's amplified, but actually this can be smaller than 1. And that will give a reduction. Cosine of omega sub 0 plus the base angle where h of j omega plus 0 by definition, that is, we replace the s, the variable s by j. Okay? This is the famous result. It's called frequency response. This is the basics of classical automatic control. This is the heart or the core of the classic automatic control. Okay. Or classic control theory. Actually, this can be done by experiment. Okay? If you have a system which is linear, then you can input a sinusoidal wave to the system. And then when the time is low enough, you measure the output. You can determine the magnitude of the signal. You can determine the phase of the signal. Then you can go back to the H of S. Then you can determine what is the transfer function H of S. Okay, we have an average H of S. Let me and then H of S is equal to the Laplace transform of the y of t divided by the Laplace transform of u of t. Okay? All right, now here is your homework assignment. Okay, here comes the homework assignment. Real homework assignment. Okay? Prove this. Homework number 1. Prove the frequency response. You can find any book, okay, regarding the automatic control. You can find any book. I think lots of books they have a proof. So you only have to look at the book and then copy the procedure in some sense. Okay? And then show me that you know how to prove it from whatever the reference is. Okay? So this is your homework for this week. You can find a book from many books about talking about automatic control or linear systems. In any book, you can use ChatGPT if you want. I don't recommend you to do that. You have to find a book by yourself. Okay? Even though ChatGPT can give you some answer, I don't think that's a good exercise or good experience. I need you to find a book in person by you. Okay, search a book, search a reference using your knowledge. Okay? And then there are lots of proofs in the books. You can find one book which is best for you, and then copy that in some sense. Write down that from the book, copy that from the book. And prove that, well, in a steady state, the output is still like this. Okay? Now, another way to say this is the following. Remember the complex number. Okay, let me. Another way to say that is the following. Now this time we use the sinusoidal wave to become complex fraction. Right? Okay, let's use the complex number, complex function directly. And then go to a stable linear system. This is a stable linear system. Again, in the steady state. Here's the output. Okay, another way to write down that is to express the y sub s of t, the steady state response. This is called the steady state. Okay. Y sub s of t is a and equal j and h of okay, so this is much more neat. That's another way to write down that. Okay. Transfer function in the frequency domain now can be written as the magnitude. Sometimes we use double bar. Okay. The magnitude. And then times the place name. This notation is the angle. This stands for the angle. Okay, this notation, okay, the triangle, and then a small curve over here. That's the angle. This is the notation used in automatic control. Okay? That's one way to write down the theorem. So one more time, let me repeat. Your homework assignment for this week is to prove this theorem. You can find any book you want. You can find any book you prefer. And then copy the proof from the book directly. That's fine. But the only point I want you to know is make sure that you know why and how to prove it. Okay? Make sure that you know why it is doing in this way to prove it, and the why and the how. Okay? That is the major point I want you to know. Right? Okay, sorry, time is up, so I will stop it. Any questions? Yeah. Sorry? Yeah? How to submit? Okay, yeah. I will open a link. I will give you an announcement later. Okay? I will tell you I have opened a link for you. You can upload the homework. You can upload your homework from the link. Okay? That will be much more easier for you, I think. Okay? Got it? Any question? Okay? Everyone? No? No question, all right? Excuse me. you use your paper to write down the homework, right? And then you can take a photo or scan your homework, and then upload the file. Okay? Got it? Write down your proof using your pen or your paper. Once you are done, take a photo or scan your paper, and then upload the file. It's better to use PDF file. Please use PDF file. Okay? Alright, got it? Alright. Okay, let me stop here and have a good evening. See you next time.